by the S invariant. Oh, okay. So this minimal genus for the knot is bounded below by the S invariant of your knot. And so for knots in the 3-sphere, this is a statement about surfaces in the 4-ball. Okay, for knots in connect sums of S1 cross S2, this is a statement about surfaces in boundary connect sums of B2 cross S2, which, by the way, also implies a similar statement about surfaces in boundary connect sums of S1 cross B3, but let me just sort of stick to this. In this case, however, this S1 cross S2 situation, we really do require, at the moment at least, a statement. We require the knot in S1 cross S2 to be null homologous in
Oh,
H1 of
sorry.
the S1 cross S2s.
Sorry, Michael. Yeah, because I
Yeah,
forgot to record your talk. Yeah, the first 5 minutes. Can you show the first page of your slide? Yeah, sounds
sure.
good.
So let me, yes.
Yeah,
So
thank
for
you,
the
thank you.
yeah, this is just a statement about, for links in
Great.
these three manifolds, we have Rasmussen invariants that control topology of the surface, and then I rephrase it in terms of genus bounds. Okay. Actually, really quickly, let me just mention very quickly, when you're proving something like this, given the previous statement, the proofs are always, I need to be able to compare the S invariant of my knot to some other sort of base knot. In the case of S3, this base knot is the unknot. In the case of the S1 cross S2s, this sort of base knot is, well, fibers, S1 fibers in S1 cross S2, or if you prefer, sort of like unknots passing through the handle. And that is sort of a somewhat more complicated computation than the unknot in S3, but we were able to do it, and we were able to get these genus bounds. Okay, so when you have genus bounds like this, let's just recall some of the famous applications of this. So in the 4-ball, well, the S invariant was able to recover the genus of torus knots. That was sort of Jake's first big result on this sort of thing, and then later on, Lisa was able to use the S invariant as well to show the Conway knot is not slice using some more tricks as well. Okay, so the RP3 case just takes a little bit more words to say kind of the same sort of thing. Okay, so for RP3, I define this sort of projective genus of a knot. So this is just the minimal genus of a cobordism in RP3 cross I from my knot to sort of the relevant unknot. Okay, because in RP3 there's sort of two cases. If your starting knot was 0 in H1, then yes, I'm asking for the minimal genus to the sort of contractible unknot in RP3. But if your starting knot was not 0, but was rather sort of generating H1 of RP3, then I asked for cobordism to the non-contractible RP1 within RP3. Okay, and this is, but in either case, I have, again, sort of a bound on the minimal genus of such cobordisms coming from the Rasmussen invariant. And in this setting, we have this kind of neat little application. I don't want to, go through it too much, but so in the case when your knot was generating H1, then you actually can have this sort of comparison. We have our Rasmussen invariant for RP3 for the knot, but you could also sort of look at the standard kind of 3-sphere S invariant for the lift of this knot. So remember, if your knot is generating H1 of RP3, then its lift in the double cover, which is S3, is also going to be a knot. And then you can sort of compare these two invariants, and we have we found some knots in which, there's sort of a difference between these things, and having differences between these things allowed us to construct pairs of equivariant knots in, the three sphere with the antipodal map, so things that would descend down to RP3, pairs of equivariant knots that are concordant in S3, but not concordant in a way that maintains this equivariance. So, sorry, I want to move this a little bit. So I write it this way down here, the concordant in S3 cross I, but not if you're trying to keep track of this antipodal map. So that was kind of neat. Okay. So, so these were what I would consider sort of traditional Rasmussen invariants. And then we also have what I would call sort of lasagna Rasmussen invariants. So I'm going to, say more about it a little bit later in the talk, but just on a base level here, okay. So we have this invariant. Chu talked about it a couple of days ago, the Kavanagh-Worley scheme lasagna module. Okay, this is an invariant due to Morrison, Walker, and Goodrich. Okay, this is an invariant of four manifold together with a framed and oriented link in the boundary. Okay, and in fact, there's in some sense many such invariants. There's one such module for each homology class that is bounded by L. Well, this fundamental class of L and H1 of L in the long exact sequence for the pair W and L. In essence, okay, it's not a huge deal. The important thing is we have a rather complicated looking statement, but I hope that it sort of makes sense as the sort of thing that you would want. So here's the statement. This is joint with Chuyu Ren. So for any second homology class that's whose boundary is L, there exists sort of this Rasmussen S invariant, which we'll call little s sub alpha of, and this is really a statement about the four manifold together with the link in its boundary. Okay, this guy could be an integer, but he could also be negative infinity, which is in some sense the worst case scenario. That's the scenario where it's telling you really no information. But so that can't happen. But so what is the statement here? So the traditional Rasmussen invariants we could have statements about cobordisms from one link to another. In this lasagna setting, because our invariants are statements about sort of a link in the boundary of a four manifold, like the most general sort of thing we could ask for, and which is true, is something like this picture. So I hope the colors make it somewhat clear. So I have W1, which is just sort of this four manifold on the left that has L1 on its boundary. Okay, and I have some alpha in second homology that's represented perhaps by some surface like this. Okay, whose boundary is the link L1. And rather than like just a cobordism from L1 to L2, I really have this very general gluing statement that from such a situation, okay, there's going to be some S invariant for W1 and L1. And from such a situation, I can glue on any sort of surface that I want over here in this, but I don't have to glue this surface onto all of L1. I can just glue the surface even to just a portion of L1 along just a portion of the boundary of W1. In which case, this surface may have some portions that are actually have boundary on this, up here away from L1. And, the resulting thing, the result of such a gluing is a new four manifold W2 whose boundary is up here. Okay. And the link L2 is sort of what I get, from gluing, I don't know, the portion of L1 that was not attached to the new surface to the rest of the boundary of the surface. Yeah, I mean, it looks complicated, but I think, if you sat down and said, what is the most general form of like gluing for such a invariant that you could ask for? It's something like this. I can glue to any portions of things that I want. There's still this little assumption, this weakly connected is again some statement that my surface, I'm not allowed to have components of my surface that are disjoint from any portion of L1. In any case, when you have a situation like this, then the topology of this surface, well, I should say that, the difference in the S invariants, and you have to be a little bit careful. The S invariant for W1 is for alpha, but the S invariant for W2 is somehow like the second homology class formed by gluing alpha and S. That's what this star is representing here. But it's just sort of like the only thing that makes sense. And then the difference in Rasmussen invariance controls the topology of this surface up to some extra factors. Okay, there's sort of, it's the topology of this surface. It's taking into account the topology of how much of this surface was actually intersecting the link, and was it really intersecting it in like full circles, or was it intersecting it in a tangle in the way that I have it drawn here? Okay, you do have to keep track of this. And there's an extra term here. This is the self-intersection of the surface using some framing information. I didn't emphasize it, but these invariants are invariants of framed oriented links in the boundary. Let me not say too much about this. I mean, this is something else that you sort of keep track of. You have sitting around to keep track of framing information. The main point is that you have Rasmussen invariants. They're integers, well, most of the time. And their differences help you control topology of surfaces, just like in the traditional case. Okay, so if you can buy that for a moment, I want to rephrase it just like I rephrased the other one in terms of genuses of surfaces in four manifolds. So if I, I think the simplest way to rephrase this one is if I have a four manifold and I fix a second homology class, okay, let's say there was no link in the boundary, okay, and let's just fix a second homology class for my four manifold, and I ask what's sort of the minimum genus of a surface that represents that homology class, then I get a bound from my Rasmussen invariant. Again, with some information regarding sort of self-intersections here that is related to framing. And this might not seem that close to the previous picture. I don't know. I mean, the previous picture had like these links and like possibly tangles going on, but I'll at least try to show the version, how do you view this corollary based on that other picture that I just drew. And it's basically this picture. There's no link in the boundary. So you just think about surfaces in your four manifold and you puncture them. And as soon as you puncture them, okay, or you puncture the four manifold near them, as soon as you do that, then you have these punctures, these B4s that you punctured. You sort of view that as the W1. And at that point, there sort of is no second homology. I mean, there's really only one second homology class, sort of the trivial class. And then the rest of the surface is viewed as sort of the S. And then, well, there's some simplification, some computation that you have to do. I tried to emphasize earlier, when you're doing the traditional versions, you need the S invariant of the unknot, or you need the S invariant of these fibers, these S1 fibers. Here, thankfully, it's very simple. You need the S invariant of this sort of unlink here, but that's a pretty simple computation. Because it's in S3s. It's in S3, so it actually matches what you already know from the 3 sphere. In any case, this is the sort of statements that we get from lasagna. And of course, I believe Chiu discussed it in some more detail, but the sort of most exciting thing for us when we were sort of defining these invariants is this fact that they can detect exotica. So there exist homeomorphic pairs of four manifolds so that you can pick a nice small alpha, a nice small H2 class in both of them. Again, the link L in both cases is just going to be the empty set, no links in the boundary. There exist four manifolds, two handle bodies, such that they're homeomorphic, but their Rasmussen invariants are not the same, so they cannot be diffeomorphic. And yeah, this was sort of our well, as far as we know, the first sort of what I might call gauge theory free or in some sense, analysis-free proof of such a result. Okay. Great. So, sorry. Do I still have control? Okay. So this was just a sort of the summary of, what the invariants more or less look like and how they're used. And now I'd like to sort of describe, so I think, Chu sort of talked about this. I think Cyprian also had a talk where he described some of these things. I'd like to try to give my take on, how we think about how one defines these things and, how maybe you would hope to define them in other situations. So first, the traditional ones, so the non-lasagna Rasmussen invariants. And I really want to emphasize, this fact that they're defined kind of in a manner that is combinatorial. It's combinatorial in a way that actually allows you to compute it, like with a computer in small situations, but in enough situations to get good results. Okay, it's combinatorially defined. How does it work? Well, what I would consider step one in the traditional setting, sort of the non-lasagna setting, is that, and this is somehow, I don't know, depending on your point of view, this is the most important step, because this is the step really where you took something that was not combinatorial and forced it to be combinatorial. You had a link in a 3-manifold, and that's just some, wobbly thing, and you force it to be combinatorial by projecting it down to some 2-dimensional projection. So P kind of stands for, projecting it down to somewhere, something 2-dimensional, and now it's a link diagram instead of a link. And that sort of makes all the difference. I mean, now it's sort of a combinatorial thing, that you can just sort of describe with essentially graph theory. Anyway, so what do you do? Well, in the 3-sphere, as I think, we're all pretty familiar, you project it down to a diagram on a disk. Okay, you use some kind of argument that you can miss the point in infinity, and so I can just put it in a disk. Okay, in connect sums of S1 cross S2, it's the same thing, except you put it in a disk together with some unknots that sort of keep track of where you would perform surgery if it was like for a Kirby diagram. I mean, essentially a Kirby diagram for S1 cross S2, where you would do 0 surgery to get to S1 cross S2. And so you keep track of that, but that's also a combinatorial statement now. I have a diagram for my link together with some unknots. And then in RP3, you project it down to RP2, the RP2 sort of sitting in RP3 like this. Okay, so all 3 of these links here are what I might call hop links. Here's a hop link in S3. Here's sort of a hop link that's playing with the handle, sort of like, making use of the handle. And I know there's 3 crossings here, but it's still the best thing I could call it is a hop link, because hopefully you can convince yourself this is a 2-component link, right? Because in RP2, we come back out to the other side. Okay. Once you have a link diagram, sort of this combinatorial data, now you sort of go one sort of combinatorial step further to build a chain complex. And this is really a chain complex that depends on your link diagram more so than your link. So let R be some ground ring. I don't really care about the ground ring at the moment, although I will in a few slides. So sort of, the original game, as described by Kavanagh, is, okay, if my diagram is in the disk, so my link was in S3, I have really 2 rules, sort of diagrammatic rules. Crossings get resolved. I think most of us are familiar with this sort of thing. This is how you build a Kavanagh complex. You can resolve it in one of 2 ways, and then there's sort of a saddle map between these 2 things. And then once you do this to all the crossings, you're left with a bunch of circles, and any circle gets sent to, well, your ground ring, adjoin x mod x squared. You assign some quantum gratings to the generators in here, okay? And you assign, okay, so this is now, sort of an algebraic sort of thing. So you need your saddle maps to be transformed into algebraic maps. If your saddle map turned 2 circles into 1, it turns into multiplication, like literally just multiplication in this ring. Okay, if your saddle turned 1 circle into 2, it gets sent to co-multiplication, there's a Frobenius algebra structure here, and there's a well-defined co-multiplication. I'm not going to write it down, but maybe what's very important here is that both of these are graded maps using these grading conventions. And well, and then you can build, this is how you build the Kavanagh complex. Okay, that's for links in the 3-sphere where your diagram was sitting in the disk. Okay, so I just sort of repeat it right there. If your diagram is in the disk, but your link was actually an S1 cross S2, so there's also these like unknots sitting around. Then I mean, there's a lot of words here, but somehow the picture, I think, says it as simply as possible. For each of these surgery unknots, you pick a disk that it bounds. That's what this DU is supposed to be indicating. And anywhere where your link diagram intersects that disk, well, you insert a copy of what I'm calling T infinity. Okay, I wrote a 2 here. There were only 2 strands going through, but you can insert an infinite twist. I don't want to say too much about what it is. Okay, I'll say a few words. It's some kind of Hoko limit of a sequence. These are sort of okay, T to the K is K full twists. This TR indicates I'm actually doing some simplifying and some truncating of these complexes. It is rather complicated. Okay, it's a rather complicated construction, but the thing I really want to point out about it is it's still combinatorial in nature. You had this combinatorial diagram, and you put this combinatorial, although infinite sort of thing, you just inserted it into this diagram, and very helpfully, when you are interested in computing homology groups, even though this is an infinite thing, you actually only need you only need to insert finitely many twists if you're interested in just like some specific homological grading. Okay, so it still does boil down to maybe perhaps infinitely many finite computations, however many you want to do. In any case, there's some procedure for doing this that is essentially you have to have some good definition for this infinite twist that I'm sort of sweeping under the rug a little bit here. So that's sort of the short version of how to handle S1 cross S2. And then, oh, sorry, so again, this idea is essentially due to Lev Rosansky. I sort of adjusted it slightly for how I was drawing the diagrams, and also just made sure I could say it easily for connect sums. And then we have Gavrichek's idea for RP2, or well, so sorry, for a diagram in RP2, which means your link was in RP3. You do the same sort of things, except now there's not just the sort of standard circle. You could also get a standard RP1, sort of the non-contractible RP1 in RP2. And this is just another circle. So you also assign this your ring adjoin x mod x squared, but you grade it differently. Okay, it's very similar to if you're familiar with annular Kavanagh homology, you know, some of your circles are trivial and some of them are essential in the annulus. You assign them essentially, you know, the same, module, but they get different grading information. And you also adjust the multiplication and co-multiplication to handle this grading properly. There's another caveat here. In RP2, you have saddles, you have non-orientable saddles, okay? RP2 is not orientable, and you can get these sort of non-orientable saddles that take one circle to one circle. So what map you assign this? Well, we're just gonna make it as easy as possible. It gets the 0 map, okay? If you're used to thinking about this sort of thing, this should worry you though, because to check that something's a chain complex and to check that D squared is 0, you have to like check something about maps sort of commuting in a giant cube of resolutions. And so if some ways gives you the 0 map, other ways around these cubes of resolutions are going to have to involve signs. So the multiplication and co-multiplication in RP2 really do have plus and minus signs that are not, well, they're complicated. Okay, they're maybe I don't want to try to spend too much time explaining them, but there are adjustments that have to be made here to make sure that you get a chain complex. Okay, so this was Gavrichek's idea. And okay, so there's the 3 sort of main ideas, I guess. And yeah, there's this issue about signs in your maps in RP2. And in all these cases, okay, you take all these different resolutions that you can get by resolving crossings, you arrange them in this giant cube, you arrange all the maps into one large chain complex that I'm writing KC of D. Again, I'm just trying to emphasize it's a statement about the link diagram, which is a combinatorial thing. At this stage, the orientation of your link, which we haven't used yet, the orientation of the link actually, well, of course, it induces an orientation of your diagram, which then induces grading renormalizations for your Ivanov complex. And then, well, and then of course, you check that D squared is 0, and you check that Radermeister moves don't change the chain homotopy type. And there, that's a summary of how you build a Ivanov complex. And if you want a Lie complex instead, then in all these cases, what do? Well, it's anywhere that we wrote Rx mod x squared, you replace it with Rx mod x squared minus 1. Okay, so x squared is 1 instead of 0. You have to adjust the maps accordingly. Multiplication is still multiplication. Co-multiplication needs some tweaking. Okay, but because of this, I mean, just because of this statement, x squared being the same as 1 means that your maps are filtered instead of graded now, and you make the Lie complex out of this instead. Okay, so yeah, that's more or less how the story goes to build your complex. And then, a very key step that I, want to make sure I emphasize. I guess I've said that a few times now, but what makes Lie homology really run is this point that an orientation of the link diagram determines a specific element in the Lie complex which survives into Lie homology. And I want to make sure I illustrate how that goes, because in some sense, this is where all the work goes if you want to generalize this to other 3 manifolds, as I'll try to show. Okay, so back in the 3-sphere, an orientation on the diagram tells you at any given crossing which resolution to use. You use the oriented resolution at each crossing, as indicated here. All right. Furthermore, after resolving all these crossings, your oriented resolution, DO, this group of circles, also inherits an orientation. That's why I still have arrows on the right-hand side of these squiggle arrows. And now, this version maybe is not how it gets presented all the time. I wanted to claim that what you do next is, remember, your oriented resolution is sitting in a disk. Your disk has a boundary. I'm claiming your next step is you choose an orientation for the boundary of your disk. An orientation for the boundary of your disk induces a preferred orientation, which I'm going to write O sub del for the oriented resolution, which would make, and this preferred orientation is the one that would make all the saddles, saddles within the resolution orientable. Okay, this is the statement where you have some circles and you alternate their orientation as you go in from outermost to innermost. Okay, I'm going to have an example in a moment to sort of make sure that's clear. But first, I want to just list some of these other things. In S1 cross S2, or connect sums of S1 cross S2, you just do the same thing. Okay, but you need to decide what to do with these infinite twists. And the answer is basically your resolution for the infinite twist is based upon what you would have done as an oriented resolution for just one full twist. But for this all to work out, you really need, in your full twist, the number of strands going upwards in the twist to be the same as the number of strands going downwards. And this is the moment at which suddenly, the original link had to be null homologous for this to be what's happening. Okay. This, by the way, ensures that the oriented resolution is going to somehow it's not going to go through it's not going to pass through the unknot, through the surgery. Okay. Meanwhile, the last step, and this is where I'll actually draw the example so that we can sort of try to understand better everything. For RP3, your oriented resolution was in RP2. Okay, and again, there's a lot of words here, but the essential idea, I think, is described in this picture. So here's an example. Here's a link diagram in RP2, oriented. Okay, so little o here indicates an orientation for the link diagram. I have a 3-component link here. And then I take the oriented resolution, and one thing I can do is take the oriented resolution and just sort of keep the inherited resolution. That's this picture. Okay, so I kept it all red. I took the oriented resolution of each crossing, and I just took the inherited resolution from the original, sorry, the inherited orientation from the original picture. Versus, I can take the same oriented resolution, so the red circles are the same down here. Okay, but now what I want to do is I want to say, okay, RP2 is not orientable, so I don't really have a priori a good way to like just say there's some preferred orientation for my circles. So what I do is I choose a curve C representing the non-contractible RP1 and RP2 disjoint from my circles. Okay, if it's available. It might not be available. Let me just say if it's available. I choose an RP1 disjoint from my circles, and I orient it in some way. This RP1 I view as the boundary of a disk. The remainder of RP2, when I take away the RP1, is just a disk. Okay, and so the orientation of this dashed curve, which I view as the boundary, induces orientations on the circles in such a way that all saddles would be orientable. Okay, so, and this is like the sense in which it's alternating. This red circle here gets oriented sort of opposite in some sense from my RP1. Okay, so that if there were a saddle between them, it would be orientable. But then the circle inside of it is oriented opposite it. This is the sense in which you alternate orientations as you work from outermost to innermost. So the blue arrows here are the orientations there. Okay, so that's something that you can do to sort of set some orientations. And now, in all the cases, okay, you had a link diagram, you took the oriented resolution, which has an orientation, but you also have some kind of preferred orientation based on what you did with the boundary. Okay, and then you just compare these two. And if they match, well, like comparing these two on each circle determines an element to assign to the algebraic structure on each circle. Okay, if they match, you put 1 plus x, and if they don't match, you put 1 minus x on each circle. That is now an element in the Lie complex. Okay, how are we doing here? Okay, so man, so let me try to push through some of this. I do want to say at least a little bit about the lasagna statements. So let's just say quickly, so having done all this, okay, the theorem is that as long as your ground ring is actually a field and 2 is not 0, okay, then Lie homology is just generated by these things, these Lie generators, okay, orientations of the diagram. Cobordisms between links induce maps on Lie homology that basically, like, there's a lot of words here, but it's basically just any Lie homology generator you just use an orientation, and then you just ask what orientations of this, if this orientation is on this link and you sort of transferred it along the surface, what orientations could you end up with on the other link? Okay, And okay, so 1 and 2 are just some kind of statement that if you ignored filtration levels, Lie homology is literally just asking what are the orientations of your link, and cobordism maps are just asking what what orientations of your cobordisms say about the orientations on the boundaries, and somehow nothing else. All right, and it's only once you put in the filtration level that you also get to say, well, guess what? The cobordism map was also filtered and had a degree that was based on the topology. Now the topology of the surface comes in rather than just its orientations. And again, I'm short on time, but let me just really try to emphasize, in my opinion, we don't know why this is true. This is a combinatorial case-by-case exhaustion check. You check all moves, all possible sort of things. There's only finitely many, and then you're done. Okay, the main point is that cobordisms can be decomposed into just sequences of only finitely many types of moves, and you just have to check them all. Okay, once you have this, then defining the Rasmussen invariant just means defining it to be a filtration level. Just maybe historically or whatever, we chose to use the average filtration level between your given orientation and the opposite orientation. Okay. So you said I have till maybe 10:45, is that right? I'm sorry, can I? Well, I'm gonna keep moving. So to talk about lasagna, I do have to talk a little bit about the definition. Okay, the definition is when you have a four manifold and a link in the boundary, we define a lasagna scheme, or just a scheme, okay, to be a surface who, not in the four manifold necessarily, but in the four manifold together with maybe some punctures. Okay, we allow some punctures in our four manifold. This means that the boundary of my surface consists of the link I'm interested in, but also maybe consists of some links in S3 down on these punctures. Okay, so that's what we mean by a scheme. And then, so basically, what do you do to define the scheme lasagna module? Okay, well, you can do it for either Kavanagh or Lie homology. I'm just going to ask you to sort of ignore this Rosansky aspect of it. This is sort of just a renormalization. The main thing to really get across is that you say, all right, scheme lasagna module is generated by schemes, okay, these surfaces that I just drew. I'm allowed to sort of divvy them up apart and just like ask for just the schemes in my given second homology class. Don't forget that I sort of fix a second homology class when I do this business. Okay, schemes that represent my second homology class together with basically just elements of the Kavanagh homology or Lie homology of, sorry, I want to go back to this picture. My elements in my scheme lasagna module are schemes like this together with just an element of Kavanagh homology down here on this S3 and on this S3, like on all the S3s, because I know how to do Kavanagh homology in S3. Okay, so I'm generated by, I mean, this is huge. There's, it's a very large, very infinite looking thing. And then there's a relation. Okay, the relation's rather complicated. It's some kind of statement that if I have some punctures that I could fit in a larger puncture, okay, then, and my scheme sort of is passing through, my scheme could have been decomposed into the part outside the big puncture and the part inside the big puncture, then I have some kind of equality between, what do I say about, the full scheme with the little punctures, sigma prime union sigma double prime, blue and green, versus what do I say about the scheme just with the big puncture, just sigma prime, okay? And the way I relate these relies on understanding what the sigma double prime would have been as a map. The star here means map in Kavanagh homology. It's very complicated. I don't want to spend too much time like, making this super precise. The point is that, uh-oh, I seem to have lost a slide. Oh, that's really unfortunate. But the point is that this is very complicated in Kavanagh homology, but in Lie homology, where if I ignore filtration for a second, all these things like elements of Lie homology and cobordism maps are literally just statements about what orientations are available. If I rephrase this all in terms of just what orientations are available on my skeins, then it becomes much, much simpler. Okay, and I get things like the following. Okay, basically, again, I have to fix the second homology class, and I just choose some scheme that represents it. And an orientation on my scheme determines a lasagna Lie generator. Okay, let me not say exactly how. Okay, but the point is that, all these things, if you ignore filtration level, they're all just statements about what orientations are available. So if you keep track of that all, then you can work out that, again, if you're in some field where 2 is not 0, okay, then the Lie lasagna module is literally just what orientations are available on your schemes. Okay, and then that allows you to say my S invariant is just going to be the filtration level of that specific orientation. Really, that specific, lasagna scheme determined by the orientation, but it's just a filtration level. And okay, I really want to make sure I end with emphasizing one last thing, and that is that this sort of definition makes it relatively easy to just show that your invariant satisfies all these gluing properties and cobordism type properties. Okay, but I hope it's clear. I skipped, in the traditional setting, I started by combinatorializing everything with link diagrams, and here I haven't done that yet. And so with this definition, there is sort of no computability. I don't know how to compute it at all. Okay, so let me just have one more slide here that is basically to compute these things at all, you need this theorem of Ciprian and Ixu that says for 2 handle bodies, okay, and we're going to skip almost all this, okay, the theorem is that for 2 handle bodies, the lasagna is computable using this K, alpha plus R, and L. This is a link diagram in the 3 sphere. You can compute everything with link diagrams for links in the 3 sphere. It's very complicated. It's some kind of code-limiting procedure as you cable the links more and more, but they're link diagrams. They're combinatorial again, okay? And so what Chuyu and I are able to work out is that this sort of game where you can do combinatorics again with link diagrams lets you compute the S invariant, again, combinatorially using link diagrams, okay? This S3 is like the traditional Rasmussen invariant. The sub R, again, is sort of a renormalization that I'm trying to avoid talking much about. Okay, and once you're here, you have sort of a combinatorial method to handle things, and you can make computations. Okay, so you have this combinatorial thing. I had a couple of points about it that maybe I'll just sort of say here. This limit, it's a non-increasing sequence in the integers, but it might diverge to minus infinity. So you can get sort of this sort of unfortunate scenario where your invariant just diverges. That point I'm sort of skipping over. This is still very difficult to compute in practice, okay, but we have some cases where we can do it, and those cases were enough to find the exotic 4 manifolds. Okay, I'm sorry for going over time, but thanks again so much for letting me have the chance to talk about some of this. Yeah, thanks everybody.